what do you think about the type of the coolants used in direct liquid cooling? Do we need dual phase coolants? Good question, and I had to prepare for that. And there is ongoing discussion in the industry about the dual phase liquid cooling, and in both immersion and direct chip. Obviously, it was kind of suppressed by the problems regarding those fluorochemical fluids, which are obviously non-healthy, or basically they cause cancer. So we don't want them, but they may be used eventually in the direct to chip cooling system because it's closed loop. It's not immersion, it's not open immersion, open bath. It's a closed loop system. So there are pros and cons regarding that one, and let's analyze that one in, let's say, regarding the few items. First of all, power density. Do we need them? Do we need even more powerful coolants than water? Water is obviously, I guess, the best coolant on the planet for now. It's pretty affordable, and DI water-based coolants are available, everywhere. And it basically means DI water, demineralized water with the additives, biocides, corrosion inhibitors, that kind of additives, softeners, and we pretty fairly well understand the water is also scalable system, so we can line up multiple rack rows, having centralized cooling systems. It's all well understood in the tons of, let's say, different applications and industries. And we have those cold plates, which reject the heat from the CPUs or GPUs. And that's this, let's say, standard cold plate, non-fancy one, just the standard one. And it can, right now, those CPUs, which are sized to the level of, let's say, 500 watts, 700 watts eventually, if overclocked maybe. But that small cold plate, 70 millimeters, 76 millimeters by 50 something, that will allow you to transfer approximately, and we're checking that one, we're calculating that one, and also testing. It will allow you to transfer with relatively high flow rate to get over 2000 watts from those small standard one cold plate, nothing fancy really. And obviously there are different advancements in that field. So for example, more complex heat exchange area, bigger heat exchange area systems, 3D printed, 3D manufactured one, and more complex builds. So that's pretty small and powerful cold plate heat exchanger. So let's find out whether we actually need more capable coolants, more exotic coolants, more challenging to maintain and to manage, to address the feature densities, which we'll find. And I was researching that topic. I found some information about the feature densities and the feature form factors of the GPU chips, so those most powerful chips. And we'll see that around 2030 we'll get those 1 kilowatt GPUs. And those GPUs, well, they are 100% more powerful compared to, let's say, most powerful CPUs right now. Let's say we have 500 watts CPUs, well, most of them are like 300, 400, whatever. But for the in the future, we'll have approximately 1 kilowatt GPUs, on the market. But the area, the size of the package, the size of the GPU would be so much bigger. It's almost 50% larger, right? So if we will assume that the current CPU cold plate is extended by the 50%, so instead of having 2.2 kilowatts rejected, it will allow us to reject easily over 3 kilowatts. 3 kilowatts of the heat rejection possible from that heat exchange area, and obviously there will be more capable, more complex heat exchange areas than this typical skewed fin design. So let's say the 3 kilowatts will be the, let's say, maximum what we can get, or over 3 kilowatts actually. But the density which we can expect is just 1 kilowatt. So my say for now is that we don't need exotic coolants. Doesn't make any sense. We just need to use the DI water. It's fairly well understood. We understand that one. It's scalable system. It's scalable cooling medium. It's cheap. It's easy to refill, replace, to manage. So that's what we are recommending. DI water with additive, constantly controlled in terms of, let's say, quality of the cooling medium with the dosing system. And that will keep you forever safe-proof for the future. You don't need to, let's say, evaluate and invest into, let's say, exotic, complex dual phase cooling systems for direct chip cooling.